my pleasure to introduce Sarah White to give the department seminar. Sarah is presently a President's Postdoctoral Fellow in the Department of Geography at UC Berkeley, and I believe her mentor is John Chang. And then before that, she did her undergraduate degree at UCSB in Geological Sciences and a master's at UC Davis in Geology. And then she went to UC Santa Cruz for her PhD, looking at ENSO and tropical Pacific over the last few million years. And she will be talking on this topic, I believe, today. Sarah, please go ahead.
Thank you. Thanks so much for having me. Let's see. Okay, so projections disagree on whether El Nino will strengthen or weaken with anthropogenic warming. And different studies find different reasons for disagreement. It's also possible that ENSO is dominated by noisy internal variability, which would mean that long-term prediction would be almost impossible. So first, if we want to know what El Nino will be like in the future, first we need to establish whether it has a detectable response to changes in external forcing or mean state. And I'll be careful with what I mean by detectable response. Once I've established that, then I'll explore what the mechanism is. How would this change in external forcing affect ENSO via sea surface temperature, winds, or so on? So I collected data for Holocene and Pliocene test cases to address these questions. First, let me remind you about the thermocline. So anywhere in the ocean will have a temperature profile that looks something like this, where it's warm near the surface and there's some surface mixed layer. It's cold at depth, and then there's a region in between where temperature is changing rapidly, and that's the thermocline. You could change the thermocline in a couple ways. You could just move the whole profile deeper so that you get a thicker mixed layer. So this would be a deeper thermocline. Or you could make the temperature gradient between the surface and the deeper waters less steep, which is sometimes called a warmer thermocline. And both of these will cause reduced vertical temperature stratification. Now for in a paleoclimate record, you'll often have data from some surface dwelling foraminifera and a subsurface dwelling foraminifera that lives at a given depth. So you'll have data from these two depths. So you can't, with this information, you can't distinguish between these two possibilities, but the effect on ENSO is similar. When you plotted those two data from those two sources, you might get something like this over time. So this part of the record is what would show a deeper or warmer thermocline and reduced vertical temperature stratification. Okay, here's a random snapshot of the world ocean. We're going to zoom into the tropical Pacific, and I'll just remind you all about how El Nino works. So during a normal Northern Hemisphere winter, which is when El Nino events peak, normally surface winds blow from east to west along the equator, and they pile up warm water in the Western Pacific, and they induce equatorial divergence of flow all along the equator, which creates equatorial upwelling. So that's happening all along the equator. But in the Eastern Pacific, the thermocline is pretty shallow. So the upwelling is able to tap into the cooler subsurface waters, and that cools the sea surface. So that sets up a about 5 degrees C temperature gradient east-west across the tropical Pacific, which then reinforces the wind pattern. During an El Nino event, the surface winds relax, which allows the warm water to slosh back into the central and eastern Pacific and allows the thermocline to relax downward deeper in the eastern Pacific. This happens every 3 to 7 years, and so this describes the El Nino Southern Oscillation. These warm sea surface temperature anomalies in the central and eastern Pacific are what I will be looking for in my paleoclimate data. Okay, also a brief review of these time periods. This, for reference, is the global benthic oxygen isotope stack. Time is going to go backward in a lot of my plots. I apologize if that's confusing. So benthic oxygen isotopes give a sort of rough view of global climate. Up is warmer and less ice, down is cooler and more ice. And you can see that during most of the Pliocene, it was warmer and there was less ice than today. It's also the most recent time that atmospheric CO2 was higher than pre-industrial and was actually similar to what we have today. During the Holocene, which is just this last interglacial period right here, CO2 was pretty stable, but insolation was changing, as it always does. So the Holocene is a good test of the effect of changes in insolation, and the Pliocene is a good test of the effect of higher CO2. Okay, my approach here is to use trace metal analyses in individual foraminifera. Why use foraminifera? This is a picture of a marine sediment core from the tropical Pacific. It's blown up over here. And it's totally gray because it's full of carbonate and lots of forams. That's what these are. So foraminifera are widely distributed in space and time, more widely distributed than any other proxy carrier for ENSO. And their shell composition, the composition of the calcite depends on the water temperature. Forams are also really useful because different species live at different depths, so you can get temperature from different water depths. More magnesium substitutes into the calcite crystal lattice at higher temperatures, and that's what gives us the magnesium-calcium temperature proxy, as you can see here. This proxy has been used on bulk samples where you crush together and average a whole bunch of forams to get an average temperature. That's been done since the early 2000s, but it's measuring individual specimens to get a temperature distribution is relatively new. Okay, so the Holocene, like I said, relatively stable with respect to ice and CO2, but insolation was changing, as you can see here, and that affected seasonality. Before I started this study, there are other ENSO proxy records for the Holocene, but it was a little unclear if the data were sort of coming together to give a general picture of there being a trend over the Holocene or not, if there is sort of just random changes. On the other hand, models are unanimous in showing that ENSO was dampened in the mid and early Holocene relative to the pre-industrial. So this wiggle is a transient model run that was run since the LGM through the pre-industrial. And I'm plotting standard deviation of sea surface temperature in the Nino 3.4 region. That's a typical way to define ENSO. So up is stronger ENSO. So you can see that there's high frequency variability, but beneath that is a long-term trend through the Holocene. And then these bars are models that were run for a particular time slice with those particular boundary conditions. All the blue ones show dampened ENSO relative to the pre-industrial, and then this one, 3,500 years, looked like the pre-industrial. So all the models implicate insulation somehow in dampening ENSO, but they disagree on the mechanism of change. So the hypothesis I'm testing is that ENSO has a detectable response to changes in insulation. And there's a couple ways that that could go. ENSO could respond mostly to local insolation, which at the equator, the sun passes overhead at the 2 equinoxes, not at the solstices. So you'd expect March or September to be the most important month for local insolation. And previous work has shown that September at the sort of end of the summer is the most important for developing El Nino event. Alternatively, ENSO could mostly respond to extratropical insolation forcing, say from June. And I'll get into the exact mechanisms for how that would work later. For now, I'll just make clear that, of course, the null hypothesis is that ENSO strength was just changing randomly over long time scales because there's so much internal variability. So what I'm looking for in my data is a trend or a pattern in El Nino strength over the Holocene that matches one of these proposed forcing time series, either extratropical insolation forcing or local insolation forcing. And if I find that, then examine what was the mechanism of change. So what aspect of the mean state matters the most? So I collected data for all of these time periods through the Holocene, and then one for the very end of the deglaciation. I collected my data here at the equator, just south of the Line Islands, which is a great spot because it's in the Nino 3.4 box, like I said, where El Nino events are typically defined by their sea surface temperature anomaly. And that's unlike many other previous ENSO records that are from the margins of the Pacific. The colors are, it's not sea surface temperature, it's showing the proportion of seasonality versus total variability. So cool colors are places where temperature variability is dominated by interannual or longer time scale variability, not seasonality. You'll see later why that's so important for my data analysis. So other circles are coral records from the Line Islands. Corals are great because you can see individual El Nino cycles, but you have to just get lucky with finding ones of an age that you want. And no one has been able to find, for this location, corals older than 7,000 years. And even throughout the Pacific Basin, there's much less data for the early Holocene than the mid-Holocene. So that's one major advantage of using marine sediment cores. I can get data from time periods with really sparse coverage. Here's modern monthly temperature profiles at my site and a La Nina event and an El Nino event. You can see that the mixed layer is pretty thick and the thermocline is pretty deep. So then the average season, this shows the distribution of monthly temperatures at my site in the middle of the mixed layer over the past 50 years. So the average seasonal cycle is in here. And then out here is the 95% warmest non-El Nino month. So then all of these temperatures out here are pretty much all from El Nino events. This is about 10% of all months. So if I'm looking at a Foram-derived temperature distribution, I can be pretty confident that the warm tail of that distribution should reflect El Nino events. And I'll just remind everybody that an El Nino event is not the attainment of a specific temperature. It is an anomaly from the mean. So I'm looking at the magnitude of that warm anomaly from the mean, even regardless of there being a mean shift. Okay, so how do I extract ENSO from marine sediments? I take a sample which spans several hundred years, and I pick out all of this surface dwelling Foram species. I cut off part of the last chamber, mount it on carbon tape, and I analyze them with UC Santa Cruz's laser ablation system. These 4 spots are averaged to get 1 representative measurement. And because the ratio of magnesium to calcium reflects the water temperature, and because each foram lives for about a month, by measuring many individuals, I can reconstruct the monthly distribution of temperature at that site at that time period. And again, the warm tail should reflect El Nino events. So I can take this Foram-derived temperature distribution from the core top, most recent sediments, and compare it to an older down core distribution. So in this example, the pink distribution has a mean warming, but there's also a change in shape. It's a narrower distribution, and the very warmest temperatures did not get as much warmer as the amount of the mean shift. So the warmest temperatures are relatively cooler in the pink distribution. To look at this in more detail, I use quantile plots. So I take the gray distribution and I calculate its coldest 2%, 4%, and so on up to its warmest 98% and warmest temperature. And that makes up all of the X values. And then I take the pink distribution and I calculate its coldest 2%, 4%, and so on up to its warmest 98% and warmest temperature. And that makes up all of the Y values. So this is a way to compare 2 different temperature distributions, and you can see what part of the distribution is different, which you can't get from some simple thing like standard deviation. So here you can see that if the 2 distributions were exactly the same, all the points would lie exactly on the 1-to-1 line. But in this example, there's that mean warming, and so all the points are shifted up off the 1-to-1 line. And so this dashed line is the 1-to-1 line shifted up by that mean shift. And then you can also see more clearly that the warmest points did not get as much warmer. Now to kind of zoom in on that, I made anomaly plots where basically this dashed line becomes the 0 line. And so now you're looking at anomalies from a uniform warming or cooling relative to the core top. And in all of my plots, the core top is always going to be on the x-axis. I always use the core top as the reference data set. So it's the same reference data set for every sample. And again, because the warmest temperatures should be dominated by El Nino events, the warmest quantiles should be dominated by El Nino events. Here you can see more clearly that all of these temperatures are significantly cooler in the older distribution than in the core top. So this is what I would interpret as showing a reduced magnitude of El Nino events. So the magnitude of that warm temperature anomaly. This method is not very sensitive to changes in frequency of El Nino events. It's very sensitive to changes in magnitude. So that's how I'm going to frame things. Now you might be wondering about the sampling statistics. What's the probability that this result or something more extreme could actually have been drawn from the same temperature distribution as the core top with the same ENSO just by unlucky chance? So I estimated confidence intervals and p-values by taking 10,000 random X, Y subsamples from the modern temperature distribution, plotting them against each other like this, and seeing how many of them gave a result that was this extreme or more so in terms of the anomaly of these uppermost points. And so points that lie below this dark gray line are significant at the p equals 0.1 level, and points below this light gray line are significant at p equals 0.05. And this overall p-value is just from the average anomaly of these top 2 points. To look at the effect of seasonality on my data, I took for each of my sites, the Holocene data are from here and the Pliocene data are from here. I compared the unaltered modern temperature distribution to an altered one where I changed El Nino amplitude or reduced seasonality. You can see that changing seasonality, even a big reduction in seasonality, it only affects the middle. It does not affect the tail of the distribution, unlike a change in El Nino. So I should not be fooled by a change in seasonality. One more bit of ground truthing, just how well does the core top compare to the modern temperature distribution? So here I've plotted the core top, the Foram-derived temperature distribution versus the modern temperature distribution from throughout the mixed layer, and they agree really well. So this shows that this species records temperatures throughout the mixed layer and the maybe very uppermost thermocline, which is in agreement with what we already knew from ecological studies of this Foram species depth habitat. Okay, here are my data. I have data from the late Holocene and several samples through the mid and early Holocene, and then one from the very end of the deglaciation, as you can see on this timeline. And there's a pattern where all the samples from the mid and early Holocene all show dampened El Nino relative to the late Holocene and the deglacial, which look like the core top. The p-values for most of these are pretty low. One of them is a bit higher, but despite that, the likelihood of getting a spurious trend or pattern, if in fact there was no change in ENSO, is really low because each of these samples are independent. Okay, so now I'm showing the Holocene data just qualitatively. Blue is dampened with respect to the core top, and this is the same as the core top. So you can see El Nino was dampened in the mid and early Holocene, and that's consistent with June insolation forcing. So here, June insolation was higher for all of these samples than for the late Holocene and core top. It's not consistent with September forcing. If that were the case, you'd expect the early Holocene to look like the late Holocene, which is not the case. So that comes back to our first research question. El Nino strength does have a detectable response to external climate forcing. I'll get into the exact mechanisms in a minute. For now, I just want to talk really briefly about that sample at the end of the deglaciation that showed stronger El Nino. Obviously, this is not explained by insolation forcing, but this is during the Younger Dryas, and there's a huge deglacial meltwater pulse at that time. And the model shows that that meltwater pulse would have forced a stronger ENSO during that time, similar to the pre-industrial, which is exactly what the proxy data show. So the models support the proxy data. Okay, so now we're ready to explore how changing insolation dampened El Nino. One idea is that the Walker circulation, so the east-west wind circulation in the tropical Pacific, that circulation was stronger because the east-west SST gradient was higher, and that mean strengthening of the Walker circulation would have quelled incipient El Nino events. So to test that idea, I compiled previously published proxy data just from average temperature from the Eastern and Western Pacific, and made some composites for the Western Pacific. In the Eastern Pacific, there's two different proxies that I broke out. And so you can see that the temperature difference between the East and the West was a bit stronger in the mid-Holocene than the late Holocene, but that's not clearly the case for the early Holocene. Alkanones would imply a higher east-west temperature gradient, but the alkanones are probably biased toward winter, the end of winter, and that's just not a time of year that El Nino is very sensitive to conditions during that time. The magnesium calcium from the Forams is either biased toward the upwelling season at the end of summer, or it represents something more like an annual average. And that data does not show a higher east-west temperature gradient than the late Holocene. So this mechanism also, you would expect this mechanism to follow local insolation forcing, because local insolation should be what's controlling the sea surface temperatures in that region. So overall, this mechanism can't explain weaker El Nino in both the mid and the early Holocene. Another idea is that the thermocline was warmer or deeper in the mid and early Holocene than the late Holocene, either because the thermocline source waters were warmer, or because there was just each year there is a seasonal deepening of the thermocline in the east due to a change in the winds. And so I found some subsurface temperature records from the Western and the Eastern Pacific. And there you can see that the mid and early Holocene had warmer subsurface temperatures than the late Holocene. Now, why would the thermocline matter for ENSO? It's because it takes part in two positive feedbacks. So if you have an anomalous deepening of the thermocline, like you have during an El Nino event, that'll cause warmer sea surface temperatures in the east, which decreases the east-west sea surface temperature gradient, which weakens the winds, which causes a further deepening of the thermocline. So this is a positive feedback. Similarly, if you have an anomalous decrease in upwelling, like you have during an El Nino event, that'll touch off the same chain of reactions and cause further decrease in upwelling. So this is another positive feedback. And these are both part of the Bjerknes feedback, which has long been known to be important for ENSO. What I'm showing is a mean state change, or what I'm talking about is a mean state change. So you can imagine that if the thermocline in the Eastern Pacific was deeper all the time, then even if it got a little shallower or deeper, or even if there's a little bit more or less upwelling, it can't it can't communicate, the thermocline can't communicate with the surface very well if it's really deep all the time. So the feedbacks still exist. They're an inherent part of the system, but they are weaker. And a weaker positive feedback means weaker ENSO. So my work shows the effect of a mean weakening of the vertical stratification on El Nino strength. Now, how do we get back to insulation? Well, one way is through the shallow wind-driven overturning circulation. So the water in the equatorial thermocline comes from the shallow wind-driven overturning circulation, as you can see here in this water tracer simulation. It comes from the sort of subtropics mid latitudes, subducts into and goes into the Western Pacific, and then it comes up as part of the equatorial undercurrent back to the surface over the course of decades. But this is actually, this picture is a little inaccurate because actually most of the water from the north is blocked by the ITCZ and the north equatorial countercurrent. So most of the water in the equatorial thermocline actually comes from the south. Now, the overturning circulation is most active in winter because that's when the winds pick up and the mixed layer deepens. And the idea is that insulation at that source location would determine the temperature of the water being subducted and drawn into the thermocline. Southern Hemisphere winter is June, and so this means that equatorial thermocline temperature would reflect June insolation. And that these time series do match up. If you ignore the deglaciation and look just at the Holocene, these time series of subsurface temperature generally match up with this Forcing time series of June insolation. So overall, we've learned that there was a pattern. There's in El Nino strength that's consistent with June insolation forcing. So ENSO does have a detectable response to changes in external forcing. And the mechanism that's best supported by proxy data is that there is a weakening of the upwelling and thermocline feedbacks due to an insolation forced warming or deepening of the thermocline. Okay, now let's go to the Pliocene. Again, the Pliocene is 2.6 to 5.3 million years ago. It's the most recent time that CO2 is higher than pre-industrial. Looking at the tropical Pacific, today there's a 5 degrees C temperature difference at these two sites, which you can see here. But if you go back in time, as these records show, that east-west temperature difference becomes much smaller in the Pliocene. And you see the same thing in the subsurface. So this is, these are temperatures in the subsurface temperatures in the Western Pacific, and then these are subsurface temperatures in the Eastern Pacific from a transect of sites, including the place where I've collected my ENSO data. And so they all show that the subsurface was warmer in the Pliocene than today. So given what we just talked about, you would expect that ENSO would have been weaker in the Pliocene because the feedbacks would be weaker. You know, the low temperature gradients would cause weaker feedbacks. However, there is some proxy evidence that ENSO was active in the Pliocene. These studies didn't quantify it relative to today, but they do show that there was some active interannual variability in the Pliocene. And model sensitivity studies have shown that, yes, the thermocline and upwelling feedbacks get weaker, but other feedbacks get stronger. And, you know, things can change in non-intuitive ways. Also, future projections are that the Eastern Pacific will warm more than the Western Pacific, causing a lower zonal SST gradient, and that will strengthen ENSO. So it's worth testing for the Pliocene whether lower east-west and vertical temperature gradients caused dampened El Nino. So again, a bit of ground truthing. Here's my Foram-derived core top temperature distribution from my Eastern Pacific site, and it provides a really good match of the modern temperature distribution in the mixed layer and uppermost thermocline, which is again what we expect given this species ecology. Okay, so I've got data from about 3 million years ago, and then every 500,000 years before that, going back through the Pliocene, so you can see on this timeline. And for all the early Pliocene samples, they all show dampened El Nino. And then by the mid-Pliocene, this sample looks similar to the late Holocene. But what if there's high frequency variability, like orbital scale, as we saw in the Holocene? So I dove into the mid-Pliocene and the early Pliocene and collected more data at higher resolution. So here's data more closely spaced in time. I should say these samples are from a different hole at the same site as these samples. So these ages may be more or less offset from each other than what I've calculated from the age model here. But suffice to say that some samples show weaker El Nino and some samples show similar to the late Holocene, relatively stronger. So by about 3.1 million years ago, there were periods of relatively stronger and weaker ENSO, or weaker El Nino. In contrast, all the samples I looked at in the early Pliocene all showed dampened El Nino. So now I'm showing just qualitatively, again, all the blue bars are my samples. Here's the closely spaced ones in the early and the mid Pliocene. And I took that previous study, the squares are another single forum study. I made quantile plots out of their data. So here's a compilation of all the data, and you can see that when the zonal and vertical temperature gradients were lowest, that's when all the samples showed dampened El Nino. And then as the zonal temperature gradient starts to get bigger, as the subsurface cools, then you start seeing alternating periods of stronger and weaker El Nino. So that's actually consistent with that model sensitivity study. They showed that even though different feedbacks, some feedbacks get stronger and weaker, overall, this sort of Pliocene state should give you something like a 50% weakening of ENSO. And they pointed to specifically the thermocline feedback as the main culprit. So looping back to our original research questions, does ENSO have a detectable response to changes in external force in our mean state? Yes. In the Holocene, ENSO responded to June insolation forcing. In the Pliocene, it responded to these big changes in mean state with lower zonal and vertical temperature gradients. The mechanism in both cases seems to be weaker vertical temperature gradients. Can explain dampened ENSO in both the Holocene and the Pliocene. And there's another study using the same approach that found the same thing for the last glacial maximum. So overall, changes in the upwelling and thermocline feedbacks could dictate El Nino strength on long time scales, which should help improve future predictions. Thank you.
Thank you. Is it questions, anyone? Maybe I can start. I have a couple.
Sure.
My first question is, does anybody know if in the modern ocean, if there are just less foraminifera during an El Nino year in the ocean? So you would think that there's less productivity, and then so your samples would be biased to non-El Nino years because there would just be more productivity, more forams would rain into your samples. I know you showed the core tops agree, but I was just wondering if that's a signal in all of this.
I don't think so, because this particular species has photosynthetic symbionts. So if anything, it would outcompete other plankton during lower productivity times when it can draw on its symbionts. Not all species are like that, but the species that was one of the reasons I chose the species that I'm using.
Okay. Good.
Yeah, Francois, could I ask a question?
Yeah, please go ahead.
Yeah, so you mentioned that the one mechanism to explain how El Nino got stronger or weaker is the east-west temperature gradient, right?
Mm-hmm.
So you mentioned when the east-west temperature gradient is low, is smaller, then you expect to have stronger. And so that I think that's what you suggest, right?
The thought for the Holocene is that if the I mean, there's kind of a, I guess there's kind of a couple ways to look at it. So one way is people who are just looking at the temperature, the east-west temperature gradient, because what they really care about is Walker circulation.
Mm-hmm,
And
yes.
they believe that the east-west temperature gradient should reflect Walker circulation. It's not a perfect reflection of Walker circulation, but it's sort of one way you would expect if Walker circulation were stronger, that would go along with a higher east-west temperature gradient. And so the thought there is that if Walker circulation is stronger all the time, that would sort of quell incipient El Nino events, because it'd be harder to have a westerly wind burst, be harder for a big El Nino event to develop.
Yeah. So that means if east-west temperature gradient is weaker, then you will get stronger El Nino. If east-west temperature gradient is smaller, is stronger, then you get weaker El Nino. That's what you are suggesting, right?
But there's another way. There is another way to look at it,
right.
depending on what you think is important. I mean, so let's see, how does this go? So the east-west temperature gradient, if you think about the zonal advection feedback, is that one of the things you're thinking about?
Mm-hmm.
The zonal advection, the zonal advection feedback is, what is it like? It's how well you can advect if you have an anomalous temperature gradient, how well you can advect that anomalous temperature gradient and sort of grow an El Nino event. And if you have a weaker existing temperature gradient, then that feedback is stronger. Is that?
Yeah. So this has been I have thought about this issue for a long time, because it can go either way.
Yeah.
And that's why I thought that maybe paleoclimate data may tell me which way is more likely to happen. I think, as you mentioned, if the temperature gradient is large, then you lock the Walker circulation to its current state. So it's more difficult to disturb the Walker circulation. Therefore, you can argue El Nino is going to be weaker. But you can also argue that when east-west temperature gradient is strong, then atmosphere-ocean coupling is more strongly tied to each other. And so whenever you change a little bit in atmospheric ocean, that positive Biakin feedback is going to intensify the intensity. So for many, many years, I thought that those way can work.
Yeah.
That's why, but I think our result seems to suggest it is more on the first argument. If the east-west temperature gradient is strong, then it's more difficult to disturb the system. Therefore, you get a weak El Nino, right? Based on your result.
Yeah.
Okay.
I mean,
No, thank you.
Yeah, that holds for the Holocene. For the Pliocene, I mean, you know, at these long time scales, the vertical temperature gradient and the zonal temperature gradient, you know, you can't tease them apart. You know, they change together. Right. And so you, like, in fairness, you could just as easily say, oh, ENSO was weaker during this time when the zonal gradient was weaker, and it got stronger as the zonal gradient got stronger. I mean, the modeling work I've seen says that the vertical temperature gradient, that strengthening that was more important than strengthening. But just if you just look at the paleo data, you can't, you could make either argument. So yeah, I agree. I've sort of like
Thank you. Yeah, no, I'm happy to find out that you have also thought about the similar controversial explanation. Yeah, thank you.
Yeah, you're welcome. Yeah.
Charlie, you want to ask a question?
Yeah, is my audio coming through?
Yeah.
Great. Thank you for explaining ENSO for dummies, because I needed that. But my question is about the long time scale assumptions that might be made. I don't know whether these can be tested or have been tested, about the stationarity of where the Forams live over evolutionary timescales, going back to the Pliocene. Do we think that those individual species that live 10 meters or 50 meters or 100 meters beneath the surface today also lived there at that time? And because pressure from new populations might cause shifts in their grazing habits. Is that something that people have looked at?
Some. I mean, it's hard to constrain very precisely, but like I said, this species has photosynthetic symbionts. So, and I'm using the same species throughout this time frame. So I think it'd be hard for it to live like way deeper in the past than it lives today and retain those symbionts.
Right. Yeah, thank you.
You're welcome. And I think as long as it's living like mostly in the mixed layer, then it's going to be sensitive to ENSO and pick up the ENSO signal. In the forward modeling I did, I drew on temperatures from the whole depth interval that they seem to match. So the whole mixed layer and then the very uppermost part of the thermocline. So if they're moving around within the mixed layer, I don't think that'll matter a whole lot.
I'll ask him one more question I wanted to ask before. Do you know if anybody's done a study to look at the water? You know, you showed those Lagrangian particles ventilating the thermocline. Has anybody looked at those pathways under a warmer ocean to see if you would draw more from the extratropics during those Pliocene? I don't know if I got the right term.
Yeah, I don't know. I was just asking Ellen Druffel if she knew anything about that. I mean, one thing that would be really interesting, like what, would the time scale of the overturning change? Would the location that it draws from change? I could imagine that, like I said, today, most of the water from the north is blocked by the ITCZ and the north equatorial countercurrent. But if the ITCZ was further south in the Pliocene, which may be the case, then maybe you'd be getting more equally water from both north and south. And so then it wouldn't be so much dominated by, you know, one solstice, like one hemisphere. Like if you're looking for an orbital signal in the data, maybe that would be like canceling out if you're getting it from both hemispheres. I've been really curious about that. I don't know if anyone has done that, but I haven't heard of it. Does anyone, I mean, does anyone else on the call know?
Doesn't seem like it, yeah.
All right.
So I'll look around for it, yeah. Patrick?
I had my, Sarah, actually, I was going to ask a question, but Sarah, what was the specific question you were asking of the people on the call?
Oh, yeah. Do you know if anyone has looked at how the shallow wind-driven overcirculation and like the ventilation of the equatorial thermocline, has anyone modeled that for a warmer or like a different, you know, climate mean state?
Yeah, modeled probably not so much that I can think of, but you can imagine that a southerly shift of the ITCZ could really change things up radically.
Exactly. Yeah, exactly. Yeah, that'd be really interesting.
My question for you was, I did not see much of the discussion of Amy Clement's work and the influence of, you know, the big question to me is not, does orbital insulation affect ENSO, but does, you know, atmospheric CO2's greenhouse gas forcing influence ENSO? And so that was what was really addressed by that early work by Amy Clement. How does that fit in here?
Well, you'd have to ask, how exactly does CO2 affect ENSO? Like it would have to work through sea surface temperature or subsurface temperature or winds or something like that, right? So I think it's still fair to look at those parameters because CO2 has to like have some sort of intermediary.
Oh no, I meant how do your results, what do your results tell us anything about CO2 influencing ENSO?
I mean, I guess broadly, the Pliocene had higher CO2 than today, and ENSO was weaker then. And so, yeah, like, yeah. And in terms of Amy Clement's work, I think that that idea was about local insulation forcing of ENSO, right? And so that would have argued like the ocean dynamical cooling, and that's all oriented around local insulation forcing. So you would expect a September timing of changes through the Holocene. Which again is not what I see. And their model was built to only, like it's only the tropics. And so they showed that like you can change ENSO. I mean, they showed that you can change ENSO with orbital forcing if you only look at the tropics. But you know, maybe that in the real world, the effect of extratropical forcing is more important, or maybe it's more important sometimes, and it's more important at the time that I studied. And so, yeah, their model couldn't have, it was built so that it couldn't have a mean state change. It was just an anomaly model. And so this mechanism of an extratropical forcing of the thermocline temperature, like couldn't happen in their model. So that's, yeah, that's, I would say that, you know, there may be times, and like I showed, you know, you could explain weaker ENSO in the mid-Holocene by that mechanism, just not also in the early Holocene. So maybe there's two different mechanisms for the two different time periods, you know.
Thanks.
Does that answer your question?
We'll talk afterwards.
Yeah.
All right, it's almost 2. Maybe we can thank the speaker again, and if you want, you can hang out a little bit and ask more questions. Thank you very much.
Thank you.